So in this section, we learn how to solve equations involving exponential functions and logarithmic functions. So there are two basic principles, which are actually, it's the same principle, but seen from a different perspective. So two basic principles. Principle number one is that if you've got an exponential function, so let's say I draw one where b is positive, okay? So maybe I should write maybe f of x, just to highlight that this is a function of x. It's a one-to-one function. Why is it one-to-one again? Well, it's a function, obviously, but because it satisfies the vertical line test everywhere, right? But it's a one-to-one function because it satisfies the horizontal line test as well. So for a given y, there's a unique x such that xy is a point on the curve. So this means that if b of x is the same thing as b of y, okay, so if well, maybe I should write x1 and x2. b of x1 is equal to b of x2. Okay, so these two expressions here are the same y values for a point on the curve. Then their x values must be the same, right? Because if they were different, let's say this is x1 and x2, the y values would automatically be different, right? I would have b of x1. So this is b of x2 and b of x1 are really different here. So because the function is one-to-one, then this is true here. So this is since f is one-to-one, or I should write an exponential function is one-to-one. And then, if we look at the inverse of that function, which is a logarithmic function, because the initial function f is one-to-one, this one is also going to be one-to-one. So again, here it satisfies the horizontal line test. So if you call that the inverse, right, which is the logarithm in base b, okay. So if I have two y values, let's say log in base b of x2 and log in base b of x1, their x values are going to be different. But similarly, if I have log in base b of x2, which is equal of x2, not x to the 2, x2, which is equal to log in base b of x1, then that means that x1 and x2 must actually be the same, okay, since a logarithmic function is one-to-one. Okay. So I'll give you an example where we use this. So for example, I'm going to use the first principle, like one-to-one. Exponential functions are one-to-one. So let's say I want to solve 3 to the 4x minus 7 equals 9 to the power minus x. Okay. If I can rewrite this in the form b to the sum expression and b to some other expression here on the other side, so this is x1 and x2. The principle says I can equate x1 and x2, so sort of get rid of the base and just keep the exponents. So on each side here, what I'd like to do is rewrite those powers so that they have the same base. And then I realized 3 is actually the power of 3, so maybe I can actually rewrite everything as a power of 3 also on the right hand side. Okay, so this is 3 squared to the minus x, and here I can multiply the powers, right? This is the power rule for exponents. And then what I have is exactly what I wanted. I've got b to d to some expression equals to b to some other expression. I can equate the exponents together. So because, okay, again, the function 3 to the x, this is a one-to-one function. So therefore, I can equate the exponents together. Right? So the exponents have to be the same if 3 raised to those exponents are equal. So 4x minus 7 is minus 2x. So I bring the 2x on this side, the 7 on the other side, and solve for x. And I get 7, 6. Okay? Or, now I'm going to solve the same problem using the other principle. Okay? I'll show you what I mean here. I've got this. Okay, here's something I can actually do. Imagine this is, all of this is x1, all of this is x2. If x1 is equal to x2, remember, this arrow goes both ways. If x1 is equal to x2, that's going to imply that log of x1 is equal to log of x2. So what I can do is take logarithms on both sides. Okay. Logarithm in my favorite base, actually. I could use base 3, I could use base, but I'm going to use base 10, so I'm just going to put log for that. Okay, so the log in base 10 of 3 to the 4x minus 7 is log in base 10 of 9 to the minus x. Okay. And then I can use properties of logarithms to simplify this. So remember that if I have an exponent like here, I can send it in front of the log. Okay. So in other words, I can recall, right? If you've got log of m to the r, this is r log of m. So I can send the r in front here. So this is what I'm going to do. 4x minus 7 log of 3 is minus 9x log of 9. So this has, and let's put this in brackets because it multiplies, all that multiplies log 3. The advantage of, why did I send the exponents in front? The advantage is that now this is going to be a number, this is going to be a number. So if you look at each side, we've got a linear equation, right? This is like minus x times a number. Okay. And here, over here, it's going to be minus 4x minus 7 times some other number. So everything is a linear equation on each, it's a linear equation because each expression on each side is linear. So I just need to solve that linear equation. So how do we do that? Well, you're going to multiply out the 4x with log of 3. So I'm going to put 4 log of 3x minus 7 log 3 is equal to minus x log of 9. And now I'm going to regroup the terms that include x together. Okay, so even though I've loaded logs, okay, maybe let's take a quick pause here. Like this expression would be just as simple to solve as if I had 4x minus 7 times 2 is minus x times 4. Okay, just as it's as easy as this, because okay, the only thing you have to understand is that I just have two numbers here. So how do we simplify this? We would, or solve for x, I mean, we would multiply the left-hand side, okay, and then eventually group the x's together, send the 14 on the other side, and divide by 12. So we're going to do exactly something like that, okay, except that instead of having 2 and 4, we've got some a log of 3, a log of 9, but it's not any harder, okay? So you just have to realize log of 3, log of 9, those are just actual numbers. So I'm going to send the x on the other side. The x log 9 on the other side, send the 7 log 3 on the other side. So regroup terms that include x and send the other terms on the other side. And now this, so this log 3, right? It's a single number, right? So if I write a log 3x, it's not the same thing as log of 3x, right? So so just maybe to make that a little more clear, I'm going to put the log 3 in brackets like that. And so you have to realize here I've got x and x that are common to both terms. In other words, I can factor out the x. And you know what? I'm going to factor it at the end like that. So I've got 4 log 3 plus log 9. So this is me. This is me regrouping my terms together. So this is like regrouping. I don't know if you have got 12x minus 4x, it's 8x. Okay. That's sort of what I'm doing here, except that the 8 is some funky expression. 4 log 3 plus log 9. And that's 7 log 3. And finally, to get what x is, I divide by 4 log 3 plus log of 9. And this is my final answer. Now, I could type that into my my calculator, okay? I would eventually get 1.16 repeated, which is exactly 7.6. Okay, I just wanted to make you realize we can actually calculate this without the use of a calculator. Okay, how do we do this? Well, I'll show you. So we can write this, the top part, and there's not much I can do with it, but the bottom part, I can write it as the sum of two logs by sending the 4 as an exponent. I can write the 9 as a power of 3 like that. We'll see that just going to make things a little bit easier. So this is 7 log 3. And now I haven't sent the 4 as an exponent. Now I've got the sum of two logs, okay, with nothing in front of them. So this is the log of a product. So this is all using properties of logarithms. So this is, and I can do the same with the 7 here, by the way. This is log of 3 to the 7 over log of 3 to the 6. Okay. Oh, actually, you know what? I didn't need to send the 7 as an exponent, so I'm not going to send the 7 back to where it was. I'm going to send the 6 in front of the log. So I've got 7 log 3 over 6 log 3. So log 3 and log 3 are common factors, so they cancel out, right? This is like 1 over, this is going to be equal to 1. So this gives us 7/6. So this is using properties of logs to simplify the answer. But eventually, I mean, if you use your calculator here, this is fine. Okay. Sometimes it's hard to recognize. You can actually simplify your final expression. But know that it's usually possible if you've got sums of logs and those end up having common powers. Okay, so you can sort of play with the rules of the logarithms to simplify your final answer. But from the point of view of getting the answer, like if you use your calculator here, I would be okay with that. I'll show you another example here. So I'm going to solve 3x equals 2 to the x plus 1. Now this is an example where I don't have a common base, and it's going to be hard to convert, or very difficult to convert those into exponents with the same base without introducing logarithms. So we won't be using principle number 1. We're going to be using principle number 2. We're going to take logs on both sides. So if logs are going to be involved anyway to convert both sides to the same base, well, we're going to take logs on both sides. Okay, and this is usually what I do when I have an equation where the variables are in the exponents. We take logs, and the advantage of taking logs on both sides is that you can send the exponents in front, and then it converts everything to a linear equation. Careful, x plus 1 is in brackets because it's going to multiply log of 2. And again, we end up with linear terms on both sides. So we're going to solve again by expanding. Regroup the terms that have x within them. Keep the other terms on the other side. Factor x. And finally, divide by that factor that we just obtained. Okay. At this point, we could use our calculator, or also you could see that the log of a difference is the log of a ratio. But after that, I'd sort of be forced to use my calculator. Calculate this, I get 1.7095. Okay. And you can always check that your answer works out. You can replace x by 1.7095 above just to see that it works. So I could calculate 3 to the 1.7095. That's 3 to the x. And that's going to give us 6.541. And then replace x in the expression on the right hand side. So 2 to the x plus 1. X plus 1 is 2.7095. And that's up to 3 correct digits. You see that those are actually identical. So it works. And here's a final example. We could solve 3 to the x equals to 2. I'm going to show you two solutions. Okay, two very simple ones. We could here first convert to a logarithmic equation, the exponential equation. So this is how we would solve those in the previous sections. So 3 to the x equals to 2. So x is the exponent to which we raise 3 in order to get 2. So you see that's converting the equation to a logarithmic equation. And log in base 3 of 2, we can use the change of base formula. This is log of 2 over log of 3. Okay, and that's going to give us 0.631. So that's solution number 1. Solution number 2, which is when I don't want to think too much, I always use that one. So we've got an expression involving an equation involving an exponential expression because x is in the exponent. So what you do is just take log on both sides, and again, taking logs will allow you to bring the exponent in front of the log, and converting the logarithmic equation into a linear equation, and then you just solve for x. So of course we get exactly the same thing we had before. So this is solution number 2. Okay, so you see in my case, when I'm dealing with an exponential equation, okay, where the variables are in the exponents of the expressions, I always take logs. So I always use this technique of taking logs on both sides, even though sometimes there's a different procedure. You see, so for this all examples, I was able to solve them by taking logs on both sides immediately. So this is really something that that's really useful, because it's going to solve like a whole bunch of different types of exponential equations. Whereas if you use this solution here, it's a bit more tricky, because you have to realize, oh, I can convert these bases into these exponential expressions into exponential expressions with the same base, and sometimes that's kind of hard to notice. But with logs, you're using a solution like this, you don't have to think too much. Actually, this is what I like about them.